they have issue.
Yeah. You said you had a question? No? Maybe somebody accidentally had their microphone on. Okay, we're going to cover 15.3 and 15.4 today. Okay, so 15.3 is double integrals in polar coordinates. Okay, so if we look at our polar coordinates, okay, r squared is equal to x squared plus y squared. Okay, x is equal to r cosine theta, and y is equal to r sine theta. Okay, then we can say that the domain here of what we would make an analogy to a rectangular region, okay, in polar coordinates, would be that the points r theta are going to go from A to B. R is going to go from A to B, and theta is going to go from alpha to beta. Okay. So R goes from A to B, theta goes from alpha to beta. Okay, makes sense. Okay, let's see what this is. Okay, let's see what this means. Okay, so and I'm going to let A be R1. I'm going to let B equal R2. Okay, so just I didn't want to put all the R's together and get really confusing, but I'm just going to say that we're going to have an R1 and we're going to have an R2. Okay, not to be confused with R2D2. Okay, but the R1 is going to be closer to the origin, and R2 is going to be farther out. Okay, so A is going to be my R1 and B is going to be my R2. Okay, R sub 2. Okay, so if we look at our polar graph, and we say, oh, well, here's a vector on, you know, my polar graph, and I'm going to call that R1. Okay, so this goes out R1. And then I'm going to have another vector on the polar graph, and that goes out R2. Okay, from R1 to R2. Well, what would be the region that I would sweep between R1 and R2 through an angle theta? Okay, through some angle. Okay, so this angle here, theta, is going from angle alpha to angle beta, right? It's going to go from angle alpha and angle beta. Well, what area is this sweeping out? Well, it would be the area between R1 and R2, okay, through this angle. So it really is this area here. Does that make sense? Okay, so if R1 only goes to this point and R2 goes to this point, then that area, that circular area, that sector, we call that a sector, okay, okay, that sector, okay, in that washer, okay, this sector of the washer here, that's the area that is sweeping out, okay? So I'm gonna say that, you know, theta goes from, you know, theta, we're gonna sweep out an angle theta here, and theta goes from alpha to beta, not zero, theta, sorry. Theta goes from alpha to beta, but R1 is less than or equal to, again, I could call these A's and B's, but I'm setting it up to do something in a second, and I just want R's. I want R's to relate the R's. So R1 is less than R, which is less than R2. But the main idea is that that's this area here, this polar area. Okay. Polar area. Okay. And so how do we define this polar area? Okay. What's the change in area, right? So if the, how would I define this area here? Well, how do I define area to begin with? Okay, what's the area of this sector? Okay, if we think of the area, okay, area of a circle, okay, area of a circle, okay, is pi r squared, right? Pi r squared, okay, that's interesting. Pi r squared. The area of a circle is pi r squared, okay, okay. But what if we wanted to relate that to theta?
Would it be pi dr d theta squared?
Well, how is pi related to theta? Okay, so how does pi relate to theta? Okay, so theta is a fraction of what? Theta is a fraction of 2 pi, right? The angle is a fractional amount of 2 pi, right? So okay, so pi is equal to theta over 2. Okay, so pi gets related to theta over 2. Now, let's think about this for a second. Okay, so the angle of a sector, think of a sector as a circle, right? Okay, why does this work? Think of this as the sector of a circle, right? Okay, a piece of a circle. Let's just say that the angle is pi over 4. Okay, and I want the area of this sector. Well, what's theta? Theta is pi over 4, right? Okay. And what is this? This is, what's the area here? The area is pi r squared. Pi r squared. But I want the sector of this, right? I want the sector based on theta. Well, theta for the whole circle, theta is 2 pi, right? So the whole circle theta is 2 pi. So I could really say that this pi over 4, okay, this pi over 4 is, it's 1/4 of, no, sorry, this is pi over 2. I'm sorry, my bad. Okay, this pi over 2, which is 1/4 of the circle, is really, we can think of it as, is 1/4 of 2 pi, right? So that's 1/4 of 2 pi. That's okay. So if you think of the whole circle, we're getting 2 pi, right? Okay, so it's 1/4 of 2 pi. So we could say, oh, okay, well, this is going to be, how do we relate theta to pi? Well, theta is equal to 2 pi, or what's pi? Pi is equal to theta over 2. Okay, so you could kind of convince yourself of that. Okay, so
I just have another quick question about the area that's shaded in red between R1 and R2. Why is it that area and not the area below, if that makes sense? Like, I feel like if it went from R1 to R2, it would be like the other piece. I don't know how to explain that.
so this guy here is the distance R1. Okay, that guy there is the distance R1. This guy is the distance R2. Maybe I'll put that in a different color. This guy here is R2, right? This guy here is R1. So what's the distance between R1 and R2? It's this guy. It's this guy right here in red. Okay, as I sweep the angle, what's this angle here? What's that angle there? That's alpha. What's this angle here? That's beta. So I'm going from an angle alpha to an angle beta, and maybe I should zoom in on this. Okay, I'm going from an angle alpha in purple to an angle beta in black. Okay, maybe I'll color code these. This is an angle alpha to an angle beta. Okay, does that make sense? And we're going from R1 to R2. So we're taking the outer one, R1, minus the inner one, R2. That's the range that we're looking from. We're looking from R1 to R2. We don't care about what happens before R1 because that wasn't in our domain. Anything less than A here is not in our domain. Okay, maybe I'll just go to R1s and R2s. I'll get rid of the A's and B's. Okay, just to make things nicer. Okay, the alpha and betas have to stay. Okay, does that help?
Yeah, that helps. I'm still just, I guess visually, I feel like it would be, like if you see it as an ice cream cone and like the red part would be the ice cream scoop, I feel like the cone, like it would be the red shaded part should be the cone, if that makes sense. Like it would still be between the angle theta and angle beta.
That's
But
only if you have this. Okay, if that was true, then that would be the cone.
right, but I mean the cone from, like the way I'm looking at it is it's a cone from still R1 to R2, but it's just like,
The whole thing?
it's like from the purple to the black line that you drew, but it would just be the inside part. I don't know how to
No,
explain that.
because this is R2 as well. Okay, I can draw a black line here if I really want to. Goes to all the way to R2.
Right. So if you look at like between those two lines, the like white part between the two lines, why is the area not that?
Because that's not in the domain. Anything less than R1 is not in the domain.
Oh, okay. Yeah, that makes sense. Thank you.
Okay, anyway, so going back to how do we rewrite this area formula in terms of theta? Well, it's just theta over 2 r squared. Okay, and you can convince yourself of that if you really want to by just turning the theta into saying, hey, theta is a fractional amount of 2 pi. Okay, that's all it is. Theta is a fractional amount of 2 pi in radian coordinates. Okay, and radians. Okay, so here's my area, right? Here's my area. So if it was the whole thing, okay, it would be 2 pi. Okay, but theta is a fractional amount of 2 pi. So pi is a fractional amount of theta over 2. Okay, so pi is a fraction. I'll write that out. Pi is a fractional amount of theta over 2. Okay, since 2 pi is a fractional amount, 2 pi is a fractional amount of theta. Okay, or theta is a fractional amount of 2 pi, is what I should say. Okay, so pi is a fractional amount of theta over 2. Okay, so let's look at the change in area. Okay, this change in area I'm going to call dA. Okay, the change that's occurring, okay, in this area. This area, change in area. Okay, so what is the area of this sector, right? What is the area of the sector? How this area is being swept out or changing. Okay, well, the change in area here, as we sweep this out from alpha to beta, okay, is going to be 1/2 R2 squared d theta. Okay, how that's changing from R2 minus 1/2 R1 squared d theta. Okay, so as theta changes, okay, as theta changes, it sweeps out this area. Okay, and how do I calculate that total area? Well, it's the sweeping out. Think of these as concentric circles. Right, we've got concentric circles. And so how is this being swept out? Well, right, we're sweeping out this area, okay, in a counterclockwise direction. Okay, whoosh, like so. Okay, and how do we get that? Well, we can sweep out the outside area of this. Can sweep out the outside area minus the inside area, right? The outside minus the inside. That's going to give me. That's going to erase that. Drawings aren't so good today. Okay, so let me go to white here. That's going to erase the inside here, right? So the outside area of the circle minus the inside area of the circle. That's how much the area is changing as the angle changes. Okay, the angle sweeps this out, and the area is changing, okay, proportionally to how much the angle changes. Okay. So the area is changing as the angle changes. That's really all you have to understand about this. The area changes as the angle changes, right? As the angle changes, it's sweeping out more area on the outside circle, and then we subtract the area that it's sweeping out on the inside circle, and we get this sector area, okay? And the reason we're doing this is because we really want to find the area of of polar coordinates, and we're going to make this thing, this dA here, we're going to make this dA. Give me my pen back. Oh, I'm writing in white. That was stupid. Okay, this dA is going to go to 0. Okay, that's what we really want here. We want to know what happens when the areas, when all these little dAs go to 0. And then we can find some really cool, integrations of polar curves. If I do a double integral, okay, then I'm going to get a volume within a polar curve. Okay, so we're kind of all setting that up here. Okay, so now what can I do? Well, I can factor out the 1/2. Okay, so dA is equal to 1/2. And then I can also factor out the d theta. This is R2 squared minus R1 squared. Okay, d theta. Okay, so now I'm going to factor this guy. Well, this guy is the difference of two squares. So this is dA is equal to 1/2 times r squared minus r1 times not r squared, r sub 2 minus r1 minus r sub 2 minus r plus r1, okay, d theta. Okay. And so I'm going to rewrite this as dA is equal to R2 plus R1 over 2 times R2 minus R1 d theta. Okay, so what is R2 minus R1? Wasn't that the change in R? Isn't R2 minus R1 the change in R? Yeah, so that's dr. This is dr d theta. Oh, that's kind of cool. Okay, and then what do we want to do? Well, we want to let this area go to 0, right? We want to let this area go to 0. Let this area get really, really small. And so how do I let the area get really, really small? Well, let's go back to my sector here. I'll make it bigger this time. Okay, let's go back to my sector. Okay, top of the drumstick here. Not chicken drumstick, a ice cream drumstick, like, okay, Icebeam was saying. Okay. Okay, and so how would I make this area go to 0? Well, I'd either have to make the angles get closer and closer together, which this really d theta is telling me that the angles are getting closer and closer together. Okay, let d theta go to 0. Okay, and so, or else what? We could make the r's get closer. So R2, let R1 approach R2. Okay, so if R1 approaches R2, then it's just one R. Does that make sense? Just a single R. So we get R plus R over 2. Okay, dr d theta. Well, what's R plus R over 2? Well, that's just R, isn't it? This isn't this 2R over 2, which is R. And so we say that dA, the change in area, is equal to R dr d theta. Now, in rectangular coordinates, we had dA equaling dy dx, or dA was equal to dx dy. Okay, this is rectangular. Okay, in polar, what do you notice? What do you notice in polar? That it's with respect to r, it's with respect to theta, but what? But because of the squared that we got in the areas, we end up with an extra r factor. Okay, so when you do your integration, your polar integration, you have to include that extra r, okay, in your integration factor. Okay, don't forget the r. And there's an easy way to remember this, and that is that this is completely laughable because it's r dr. Okay, or what I like to say, hardy har. Okay, I'm just funny like that. Okay, so hardy har, or rdr d theta. Okay, hardy har d theta. Okay, you're just laughing. You're laughing at your d theta. It's rdr d theta. Don't forget the r. If you forget the r, you're going to screw up your problems. Okay, you need that extra r because of what we showed here in trying to calculate the change in area. The change in area is based on a change in r, a change in theta, but it also has this extra r value. Okay, the change in area is with respect to r. Okay, and that shouldn't be counterintuitive. Okay, why? Because the further out you are, the bigger your arc is. Does that make sense? That where you're at on where your r is at depends on the area that's being swept out. If you're closer to the origin, right, that's a smaller area. Oops, go back again. Okay, I'll make it substantial. That's a small area, right? Okay, if you're further out from the origin, then it sweeps out a larger area. Does that make sense? So the rate of change here is proportional to how far away you are from the origin. Okay, you're going to get more change the further out you are. Less change the closer you are. Okay? So just chew on that. The main idea here, you don't even have to know any of this stuff, except don't forget this R. If you forget this R, okay, I'm going to have your mom like smack you or something. Okay? So don't forget the R. Okay? It's necessary to do the problems. Okay? Okay, so if I want to convert, if I want to convert a rectangular problem, okay, into polar coordinates, well, what do? Well, I change, okay, the X's and Y's into R's and thetas. Okay, actually, I'm going to do it like this. I'm going to go X is equal to R cosine theta, R sine theta. Okay, but then what do I need? What is dA? dA was dx dy, or dy dx. But now what is it? Well, it's r dr d theta. Boom. Okay, where this guy is going to be a function of r as a function of theta, r1 theta. This is r2 theta. Okay, and then this theta is going to be a function of alpha beta. Okay, just like we did in rectangular coordinates. Okay, and this is not a 0 again. This is theta. I don't know why I keep doing that. Okay, so this is r1 theta to r2 theta. Okay. Okay, let's just jump into this and let's do some stuff. What are you not supposed to forget? Don't forget the R, RDR. Okay, hardy har, har, hardy har, har, har. Okay, number one. Okay, evaluate. Okay, 3x plus 4y dA. Okay, over R, when R is the region of the upper half plane, I should say, plane bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. Okay, so let's draw out what R is here, and then we'll convert everything and we'll integrate. Okay, this is y squared, sorry. Okay, so let's look at, what's x squared plus y squared plus equals 1? Isn't that the unit circle? Okay, that's the unit circle. 1, 2, 1, 2, 1, 2. So we've got the unit circle. Okay. Unit circle. Okay, we've got the unit circle. Okay, and then what's this? This is a circle of radius 2, right? So we've got double the unit circle. Okay. I should have drawn my circles first and then put my marks. But whatever. It's all good. Let's see if I can erase this one real quick. Nope. Whatever. But what? We only want the upper half plane. We only want this guy here. Okay, this part of the washer. We only want the upper half of the washer. So the bottom half of the washer, it doesn't exist. So I'm going to get rid of this non-existent bottom part. Okay, makes sense? Say goodbye to that part. So this is the area that I'm integrating over. Okay, this is the area that I'm integrating over. Oh, well, that makes sense that I'd want to use polar coordinates for this, right? I wouldn't want to use rectangular coordinates. I'd have to have two integrals, one going from, well, the limits of integration would be a nightmare here. I'd have to have the square root of 4 minus x squared plus or minus, okay, minus the square root of 1 minus x squared plus or minus. I'd have to subtract those two. Okay, that would not be fun. Okay, and what would be plus or minus? It would only be plus because we're talking about the upper half, but still you're going to end up with y equals 2 square root functions. No, not fun. Okay, so let's convert this to polar coordinates. Okay, so how do we convert this to polar coordinates? Well, we're going to say 3x. Well, what was x? Well, this is 3r cosine theta. Okay, plus 4. Well, what's y? Y is r sine theta, and that's squared. Okay, and then what do? It's r dr d theta. Okay, so what's r going from? Well, r is going from 1 to 2. Oh, that's easy. And what's theta going from? Well, that's 0 to pi. Well, that's easy too. Okay, well, that's kind of cool. Okay, so what I'm going to do is I'm going to simplify this. I'm going to multiply this out and then distribute the r. So this thing becomes 3r squared cosine theta plus 4. This is going to be r squared sine squared. So this is actually r to the third sine squared theta dr d theta. Okay, so I'm going to integrate this guy. Now 1 to 2, 0 to pi. Okay, so now we're going to do the integration with respect to r first, right? So integrate with respect to r. Okay, so this becomes r cubed cosine theta plus r to the fourth sine squared theta. Oh, that's kind of cool. Okay, from 1 to 2. So now we're going to plug in our r's, right? Okay, so this is going to be 2 cubed cosine theta plus 2 to the fourth sine squared theta minus 1 cubed cosine theta plus 1 to the fourth sine squared theta. Okay. So this is going to be 8 cosine theta minus 1 cosine theta. That's going to give me 7 cosine thetas. This is going to be 16 sine squareds minus 1 sine squared. That's going to give me 15 sine squareds. Okay, cool. And then that's all with respect to theta now. We got rid of the r. Oh, okay, so 0 to pi. Okay, nice. So now let's integrate with respect to theta here. Okay, so this guy's going to be 7 sine of theta. Okay, 15 sine squared. Well, how do I integrate with respect to sine squared? Oh yeah, I'm going to use a half angle. I remember from Calc 2 that I could use a half angle formula here for this guy. Okay, so I was like, oh, okay. So this is 1 minus cosine 2 theta over 2, I believe, right, times 15. Okay, that's what that guy is up there. Okay, so plus, I'm going to say the integral from 0 to pi, and this guy's this guy was already integrated. So 0 to pi d theta. Okay. Nice, nice, nice. Okay, so this is going to be 0 to pi of 15 over 2 minus 15 cosine 2 theta over 2. All right, or I could pull the 15 out in front. It really doesn't matter. Okay. D theta. And this guy, okay, well, what's 7 times the sine of pi minus 7 times the sine of 0? Okay. Well, isn't the sine of pi 0? Yep. Isn't the sine of 0? Isn't the sine of 0, 0? Yep. So that whole thing just goes to 0. That's gone. So now we're just left with this guy here. I could factor out a 15 halves if I wanted to. Maybe I should have done that instead of multiplying the 15 halves. It doesn't really matter. Okay, let's just leave it. Let's just leave it. This is going to be 15 halves theta, right? Minus 15 halves sine of 2 theta. But if I did a u du substitution, I would have to divide by 2. Okay, does that make sense? I'd have to divide by 2, which would mean that it would be times 1/2. Okay, on that. Okay, and then that's going to be evaluated from 0 to pi. Okay, but once again, if I plug in pi here, well, isn't that going to give me 2 pi? What's the sine of 2 pi?
0.
0, yeah, thank you. Thank you, Wu. Okay, and then what's the sine of 0? Plug in the sine of 0. Isn't that 0 as well? So this term does not survive. That term just goes away. What about 15 halves times pi minus 15 halves times 0? Well, it's 15 halves times 0. That's just 0. So the only thing that survives here is 15 pi over 2. That's it, and that's the answer. That's the answer to the volume under that region. Hi, what's up? Cool. Oh, and they're going to send you you took the test and everything. Okay,
Yeah.
awesome. Perfect.
So now I'm just waiting for the thing, certificate.
Okay, so we just have to get we'll have to make a DMV reservation.
But I need to study.
Take the actual test.
I'm really scared because
Oh, it's easy. Yeah, just get the book from Josh.
I have the pamphlet
Oh,
that
okay.
you gave me
Okay.
in my room.
Okay, sounds good. Thanks.
Have fun with your class.
Thank you. Sorry about that. That was my 16-year-old daughter. She's wanting to drive a car, which is pretty scary. So.
Can you scroll down a little bit?
Yeah, sure. Absolutely.
Thank you.
There you go. Okay. Number 2. Okay, find the volume of the solid. Okay, bounded by the plane. Z equals 0. And the paraboloid Z equals 1 minus x squared minus y squared. Okay. Oh, interesting. Okay, so when x and y are 0, z is 1, right? Z is 1. So what is this paraboloid they're talking about? Okay. It's kind of the top half, you know, of kind of a dome shape. Looks like this. Okay. So when z equals 0, okay, or sorry, when x and y are 0, z is 1. Okay, so we know that the top of the dome is going to be at 1 here. Okay, what happens when z is 0? When z is 0, don't I get just a unit circle? Yeah, when z is 0. So x and y equals 0. Then z equals 1. When z equals 0, then I get x squared plus y squared equals 1, which is just a unit circle. Okay. Get this thing here. Okay. I really like that. Let's do it more like this. Okay. And then we're getting this paraboloid through z there. Okay. So this is the base. Okay. And get this paraboloid shape going. Okay. So I want to change this to polar coordinates. Okay. So I want to know why. Because what's the base here? The base area is the unit circle. That's the base area. Okay. R is the domain is in the xy plane, which is the unit circle. R is the unit circle. X squared plus y squared equals 1. That's R. That's R. Or less than or equal to 1, I should say. Okay, that's the domain. Okay, we could say this is xy such that x squared plus y squared is less than or equal to 1. Okay, so that's how you want to do that. Okay, but that's a circle. That lends itself to polar coordinates. Why? Because how do we represent the unit circle in polar coordinates? It's just r equals 1. It's all the points such that r is equal to 1. Okay, in polar coordinates, this would be, okay, r theta, this would be 1 theta. Okay, that's the domain there. All values, okay, well, it would actually be, it wouldn't be, that would be a circle. If it's out at 1, it's just all, it's everything, it's r theta, right? R theta, okay, changed to polar coordinates means that what? Means that theta can go from 0 to 2 pi. Well, let's look at r. R goes from 0 to 1. Okay, and theta goes from 0 to 2 pi. Oh, okay. So instead of dealing with this guy, I can actually deal with these guys, which are just numbers, which are just values. So that's what I'm going to integrate over. Oh, okay. I'm going to integrate over dr d theta. Okay. So we had the function in terms of x and y, right? We have the function in terms of x and y, which is 1 minus x squared minus y squared. So I could put that here, f of x, y. Okay. And then I'm just going to put d for domain. Okay. And then dA. And how am I going to change this? Well, this is going to become, okay, f of x cosine theta, y sine theta, r dr d theta, okay, over this region, okay, in polar coordinates. Okay, you can call it r if you want, you can call it whatever. Okay, but I do know what that region is now. The dr r's go from 0 to 1. The d thetas go from 0 to 2 pi. So that just lent itself nicely. Okay, so what was the original function? The original function here, okay, was z is equal to 1 minus x squared minus y squared. Oh, okay. Well, how could I change that into a polar function? Well, isn't x squared plus y squared equal to r squared? Yeah, so what happens if I factor out the negative sign here? I would get z equals 1 minus x squared plus y squared. Wasn't that just 1 minus r squared? Yep. So this is 0 to 2 pi, 0 to 1 of 1 minus r squared times r dr d theta. Oh, okay. So now all I'm going to do is distribute, and I get r minus r cubed dr d theta. This is 0 to 1 and 0 to 2 pi. Okay. And so this becomes r squared over 2, minus r to the 4th over 4 evaluated from 1 to 0, okay? And you could easily see that this is going to be 1/2 minus 1/4, which is 1/4. So this becomes 1/4 d theta from 0 to 2 pi, okay? And then what's 1/4 d theta? Well, that's just 1/4 theta evaluated from 0 to 2 pi. And so that's just 2 pi over 4 or pi over 2. Oh. You know what? That deserves my easy button.
That was easy.
That was easy. Okay. That was easy. Now, what happens when the region isn't so nice? What happens when the region isn't nice and circular? Okay. What happens if the region looks like, I don't know, let's say that we want to integrate under this curve, but the region looks like this, okay? Not so nice, right? Not so nice. Can we still do polar coordinates? Well, absolutely we can. We just need to get this guy, this area in terms of a function of theta, okay? We need to get this area, okay? We'll call it D. We need to get the domain in terms of, you know, r of theta, okay? So we just need to get in terms of a function of theta, okay? How is this thing moving along? How is this, basically this vector tracing out this area, right? As theta moves, how does r move? R is going to be dictated by theta, right? So as we kind of like trace this thing out, how does r move with respect to theta? Okay, theta is the independent variable, r is the dependent variable. And it's going to sweep out this area that we're integrating over. And then we're going to be like, oh, yeah, on this, and then what's the volume under this little mapping here, right? So what's the volume of that cylinder under that mapping, okay, under that surface? Cool stuff, okay? It's a lot more complicated than just the area under a curve, right? Area under curve, we'd be like, oh, boom, boom. And then we say, oh yeah, this is the area under curve. Just integrate, right? So here we're taking this area and we're integrating under a three-dimensional surface. So to find the volume of that cylinder. Okay, so fun stuff. Okay, number 3. Use a double integral to find the area of one loop I need my water. This is the water checkpoint. Okay, we're halfway through today's lecture. Water checkpoint. You have some water, go ahead and grab it. Drink up. Okay, use the double integral to find the area of one loop of the four-leafed rows r equals cosine of 2 theta. Okay, so now we know, oh, okay, this four-leafed rows that looks like this, okay, it starts off here, and it goes, it's a four-leafed rows. So let me make sure I get this right. So since it's a four-leafed rows, it's going to look like this. Did you like that? Wasn't that awesome? I mean, you could like reverse, you could like rewind the tape, and then you could just be like, oh, that's how that's made. So that's how that's made. Okay, it's if you want me to put arrows on it, I can. Okay. Okay, and that's how that guy is made. Okay. So, and it goes out to 2 because I know that when cosine is, or sorry, it goes out to, what does it go out to here? It goes out to 1, right? Because cosine of 0, 2, 0, yeah, it goes out to 1. Okay. And when theta is 0, we're out at 1. Okay. So 1 there. Okay. So now, what do we know? Well, we want one loop of this thing, right? We want to find the area of one loop. Okay, so here's what I'm going to do. If I start with theta equals 0, I'm right here, okay, at this point here. Okay, so, and then how would I get back to 0? What would give me a value of 0 here? Cosine of 2 theta. What would theta have to be to get me 0? Well, I know that cosines are 0 at pi over 2, right? So cosine is 0 at pi over 2. So r would be equal to 0. Okay, if I do cosine of pi over 2, I would get 0. But I have to multiply something by 2 to get pi over 2. Well, what would I multiply by 2 to get pi over 2? Well, how about pi over 4? So the cosine of 2 times pi over 4, that has to be 0. Oh, okay. So I know that this is going to go from 0, the top half of this leaf, okay, or this petal, we just call it petal because it's petal of a rose, right? The top arc of this is going to go from 0, okay, to pi over 4. What's the bottom arc going to go from? Well, we could say that it goes from 11 pi over 4 to, is it 8? No, 7, sorry. 7 pi over 4 to 2 pi if we wanted to. Or we could be kind of sneaky and say that this actually goes from negative pi over 4 to 0. Okay, that bottom one is negative pi over 4 to 0. So if I wanted to draw the whole thing, I wanted to draw the whole petal, well, what would I do? I would go from theta of negative pi over 4 to, okay, to what? To pi over 4. Okay, so that gives me my d theta. Okay, what's r going from? What's r going from? What's r allowed to go from? Well, what's tracing what's tracing any? Let me use a different.
0 to 1.
You would think it's 0 to 1, but it's really not.
0 to cosine to theta.
Because 1 is not. It's not always 1, right? It's not always 1, right? What's dictating how far out we go? Well, it's the function, right? It's the function. So think of it like this, okay? Remember when we went back to, let's go back to the ice cream cone, right? Go back to the ice cream cone. All right, and we want, you know, a sector, right? Well, in this case, right, what's dictating this sector that's sweeping out? Well, we don't even have this scenario, we have this scenario here, right? Does that make sense? Okay, so say this is R, right? And so what's sweeping out this entire area here? Well, it's all of my values of cosine 2 theta. Isn't that sweeping out all of those values as I go around? How far out is R? Oh, right, and it's sweeping that area. So it actually goes from 0 to cosine 2 theta. R is a function of theta. Okay, r is a function of theta. It starts here at 0. At negative pi over 4, it's 0. That's r. R at negative pi over 4 is 0. And then it starts sweeping out, okay? And it's dictated by that function, how far out my vectors go, okay? Sweeps out the whole thing, okay? And so now we want the volume, right? We want what? We want to find the area. We just want to find the area of this. Okay, so if I want to find the area of this, what can I do? Well, I can let the function be equal to 1. Why is that? Why would I let the function be equal to 1? Because it's very convenient. I'll let it be equal to 1 r dr d theta. Don't forget your r. This is r dr d theta. Okay, hardy har d theta. Okay, now why would I want 1? Okay, because 1 times anything is itself. It's very nice. And what does this mean? This is the plane z equals 1. This is the plane z equals 1. So what I would do is I would superimpose this guy here on a plane z equals 1. Okay, 1 high. And so the volume and the area are going to be the same. Let me say that one more time. If I superimpose this on something that's 1 unit high, right? Wouldn't the volume and the area be the same? Numerical value? Does that make sense? Why? Because aren't you just going to end up multiplying by 1? Aren't you going to find the base area and then multiply by 1 to get the volume? If z is equal to 1. Okay, and in this case, what are we doing? We're superimposing, okay, this 4-leaf rose okay, on this, and then we're going to go down 1 unit. Okay, so how do you find the volume of that column? Well, isn't it the same as the numerical value of the area multiplied by 1, by a third unit? Does that make sense? Maybe, yes, no, maybe.
Oh, I'm just a little bit confused, but I might have just missed something because my audio was cutting out a bit. How did you get z equal 1? Or like, why are we using that?
Again, we're using z equals 1 because we're saying that instead of this being on the xy plane, we're going to go up 1 unit and we're going to find the volume now. Okay, the volume of this 4-leaf rose superimposed on a plane of height 1. Because once again, what's the difference between the area of a circle, okay, and the volume of a cylinder of height 1? Well, the value is just, the numerical value is the same. Okay, say that this was 16 pi units squared. We'll say feet squared. 16 pi square feet, okay, is this area. What happens when I multiply it by a height of 1 foot? Doesn't it just become 16 pi feet cubed?
Oh, okay, yeah, because I see. Okay, thank you.
Does that make sense?
Yeah, thank you.
So we're adding that third dimension, but we're letting that third dimension be 1. Make sense? Make sense? We're including the third dimension, and so we're just saying, look, I can find the area of this thing by doing a double integral and just letting the function be equal to 1. It's the same trick that we use when we do a single integral and we want to find the area of something, okay, or the distance of something, okay? So it's the same thing that we want to find the length of something. Okay, we let the function be equal to 1. Why? Well, what happens when we let it, say that we have, I don't know, from 1 to 2 of x squared, okay, or not x squared, of 1 dx, right? So we go from x 1 to 2, right? So, right, so what is this? This is x, evaluate from 1 to 2. Well, what's this? This is the distance between 2 and 1. Maybe I should have used it. Let's use a 3 here, I guess. Okay, isn't this the distance, the linear distance between 3 and 1? But what did we actually find? Because aren't we going to subtract? We're going to go 3 minus 1 is equal to 2. And that's 2, we could say 2 feet. Right, so 3, 1, that's 2 feet apart. Right, that's linear distance, but it's also area. Because what do we do when we integrate? Well, we integrating where are we integrating? We're integrating when y equals 1. So what are we doing? We're actually doing this. We're saying, oh, when y is equal to 1, we're going to integrate this and find the area between 1 and 3. Oh, well, how do I find the area between 1 and 3 under the line y equals 1? Oh, well, isn't that just 2 times 1? Isn't it just 3 minus 1, which is 2? And 2 times 1 is 2. So this would be 2 square feet. The area is 2 square feet. The linear distance is 2 feet. It's the same analogy. Okay.
Professor, I have a question about the bounds for the one that has from pi over 4 and negative pi over 4.
Yeah.
Would we be able to go from 0 to pi over 4 and then just multiply it by 2 since it's symmetric?
Yes, you would.
Okay.
Yes. Okay, so let's do this. Let's do this one. So this is going to be negative pi over 4 to pi over 4, and 0 to cosine 2 theta of r dr d theta. Okay, so this is going to be r squared over 2 from 0 to cosine 2 theta. So this becomes cosine squared 2 theta all over 2. Okay, d theta. Okay. Interesting. Okay, and that's from negative pi over 4 to pi over 4. Okay. And yeah, with respect to theta, I mean, yeah, there's going to be some symmetry here, but okay, negative pi over 4 to pi over 4. Okay, and so now we got to figure out, well, how do we deal with this guy? Let's see. Let's use that half angle identity again. Okay, so for cosines, I'm going to pull this out. This is 1/2. Cosine squared 2 theta is 1, okay, 1 plus cosine 4 theta over 2. Okay. So I haven't integrated yet. I've just changed this using a half angle identity. Okay. So, okay, because cosine squared theta is equal to 1 plus cosine 2 theta over 2. Okay, so, but in this case, we have 2 theta. So I had to replace theta here with 2 theta, which makes it 4 theta. Okay. So now what can I do? Well, I could pull out the 1/4 here, put it in front. Negative pi over 4 to pi over 4. I could go 1 plus cosine 4 theta, d theta. Okay. So what's this guy going to be? This guy's going to be theta. What's this guy going to be? This guy's going to be 1/4 sine of 4 theta. And you can, again, you can prove that to yourself if you really want to by doing a u sub. But I just know that if I do a u sub on 4 theta, I'm going to end up with 4 d theta, and then I'm going to divide by 4. Okay. The opposite of multiplying by 4 here is division by 4. So just know that it becomes my u du. Okay, and then negative pi over 4 to pi over 4. Okay, and so I'm gonna plug this guy in. And what am I gonna get? I'm gonna get 1/4 times pi over 4 plus 1/4 sine of 4 pi over 4. That's the sine of pi. Well, what's the sine of pi? 0. That goes away. Minus 1/4 times negative pi over 4. Okay, cool. Okay. Plus 1/4 times the sine of negative pi. Well, this is 4 times negative pi over 4. Sorry, that's really bad. The sine of 4 times negative pi over 4. Okay, so that's the sine of negative pi, which is also 0. So that goes to 0. So this becomes pi over 16 plus pi over 16, which is pi over 8. Well, done. With that one. Let's do an application of this. Okay, 15.4, applications. What the heck? Move this over. Okay. 15.4, applications of double integrals. Okay, applications of double integrals. Okay, so density and mass. Okay, so I could have a density function, which is, this is really rho. I don't know how to draw rho real well. So this is rho. It's a Greek letter rho. It's just going to look like a P. Okay, just P density. It's going to look like a P because I don't really want to spend the time trying to figure out how to draw rho really nicely. It really kind of looks like this guy, I think, but I don't want to spend the time drawing rho every time. And it's just going to, I'm just going to screw it up anyway. For some reason, I just can't ever, I can't, oh, that's a nice one. But it looks like E. This looks like E. So this is very confusing. So in this case, in this class, it's going to be P. So rho is P. Okay, so just deal with it. Okay, so the density, okay, is equal to rho of xy, which is equal to the limit of delta M over delta A. Okay, it's the mass over the area. It's the change in mass over the change in area. It really is the change in mass over the change in volume, but we'll get to that a little bit later. Okay. Okay, the total mass the total mass of the lamina as the limiting value of the approximations okay, M is equal to the limit as K and L approach infinity of the summation of I equals 1 to K and J equals 1 to L of rho times our rho evaluated at xij star, yij star, delta A. Okay, so this is equal to the double integral over a domain of rho of xy dA. Okay, so that's density. This is your density function here. Okay, so mass over volume. But again, this is not uniform density. This is when density changes. Think of it like a rod, okay? A rod that's made out of different materials, okay? You have this rod, okay, but it's not made out of uniform metal, okay? Maybe parts of it are cobalt, maybe parts of it are steel, maybe parts of it are nickel, maybe parts of it are tin, maybe parts of it are aluminum, okay? And so you're saying, as I move along this tube, okay, along this rod, the density changes depending upon where I'm located in XY space. My density is changing. So how could I find the density of the whole rod? Oh, we're gonna do a double integral. Okay. Likewise, the charge distributed, the electronic charge distributed, okay, over a region, okay, is given as Q equals, oh, this was M, by the way. M was equal to that. That's the mass. Okay, is equal to the double integral of the density as the area changes. Okay, Q, the total, this is total mass, and this is total charge. Total charge is given by sigma of xy dA. Okay, so some function that tells me how the charge is distributed. Okay, and that gives me the total charge. Okay, so let's see what this is. Number one, a charge is distributed okay over a region such that sigma xy is equal to x times y. Okay. Where D is the following triangular region. Okay, so it looks like this. Oops, not like that. Like this. Okay, that's the region. That's the origin. Okay, X and Y. Okay. And so, how are we going to find the total charge? Find total charge. Okay. So we know that we have a region here, X, that it's going to be integrated over. Okay, the X's and the Y's. Okay. Okay, and then sigma xy. Okay, dA. Okay. Well, what was sigma xy? Well, that was xy, and then we're going to go dy dx. Okay. That way, I'm going to take vertical slices here. Okay, if it's dy dx, I can take vertical slices. Let's do a vertical slice here. Okay, and so what's the equation of the bottom line here? What's the equation of the bottom line if this goes out to 1? Okay, and this goes up to 1. Okay, well, the equation of the bottom line is, this bottom line is y equals negative x plus 1. What's the equation of the top line? Well, that's y equals 1. So we know that this goes from negative x plus 1, or 1 minus x, I'll do 1 minus x, okay, to 1. And then what do the x's go from? The x's go from 0 to 1. Okay. So let's put that together. 0 to 1, 1 minus x to 1, xy, dy dx. Okay. So integrate first with respect to y. This becomes xy squared over 2 from 1 minus x to 1. So this becomes x over 2 minus x times 1 minus x squared over 2. Okay. So this becomes x over 2 minus x over 2 times 1 minus 2x plus x squared, squaring that out. Distribute the x over 2, so x over 2 minus x over 2 plus x squared minus x cubed over 2. Okay, so those cancel. Okay, and so now I want to integrate this. What? I want to integrate this from 0 to 1 dx. Okay, so this becomes x cubed over 3 minus, this is x to the 4th over 8 from 0 to 1. So this just becomes 1/3 minus 1/8, which is 8/24 minus 3/24, which is 5/24. Okay, and charge is measured in coulombs. Okay, and so it's 5/24 coulombs is what the total charge is over that area. Okay, total charge over that area. Okay, let's talk about moments and center of mass. Okay, so moments and center of mass. Okay, the moment of the lamina about the x-axis. Okay, and when you think of lamina, just think of like surface. Okay, like laminate flooring, right, is a surface. It's you laminate this. Okay, it could be a curved surface. It could be, okay, you know, a flat surface. Just think of it as surface. Okay, the moment of a lamina, okay, a surface about the x-axis. Okay, about the x-axis. Okay, is the double integral d with y times rho xy dA. Okay, so that's about the x-axis. Okay, about the y-axis is dx. So notice that they're opposite. About the x-axis is y rho dA, and this is y-axis is x rho dA. Okay, the center of mass, let's think of this lamina here. Let's think of this lamina. Okay. We have a point xy here. Okay, and the center of mass okay, is where if you tried to balance this at that center of mass, which we call x bar, y bar. Okay, it's the average of all the x's, the average of all the y's. Okay, in 2 space. Then if you were to try to balance this thing and spin it, it would spin. Okay, it'd be perfectly balanced. Gravity's pulling down on this equally, and it's balanced. Okay. Okay, true story. True story. Although I guess gravity really doesn't pull down. It really is just relative to your perspective. So, but this is not physics class, so we won't get into the theory of relativity in this class. Okay. Gravity is a figment of your imagination. Okay. Although it hurts. It does hurt. Okay. Because you are constantly accelerating toward the ground, or the earth is constantly accelerating against you. I don't know. Again, it depends on your frame of reference. So who knows? Okay, the center of mass, okay, is defined as x bar, y bar, okay, such that, okay, the moment of x bar is equal to the moment of y. Okay, and okay, so which one was the moment about y? Well, it was this one here. This is the moment about y, and this is the moment about x. So the moment about x bar, moment of x bar is the moment of y. So again, the variables get a little confusing. The moment with respect to y bar is equal to the moment about x. Okay, the moment about x. Okay, so what can we say? Well, we can say this, that no, sorry, I did this wrong. This is not the moment. This is mass. This is little m. This is the mass times x bar and the mass times y bar. Okay, because think of this as a point mass. Think of this as a point mass. You've got all your mass in this one point. And we're saying, oh, okay, the center of that, okay, the mass at x bar and the mass at y bar in this one point mass, okay, is the equivalent to all of the mass of all the other points on this thing, right? X1, X2, X1, Y1, X2, Y2, X2, Y, right? We're equating all of that to the moment of X, okay? So we're gonna say that what? We're gonna say that X bar is equal to the moment at Y over M, and Y bar is equal to the moment of X over the mass, okay, which is equal to 1 over the mass times the integral, okay, of, what was the moment of Y? Well, that's with respect to X and rho of XY dA. Okay, so X bar goes with X, okay, and the Y bar is 1 over M times Y rho of XY dA. Okay, so this is going to be, I mean, you can kind of get rid of this middle term here, but just think of it, you know, in these terms here. X bar is with respect to X, 1 over M, and Y bar is with respect to Y. Okay, where M is equal to what? Well, M is equal to, this goes back to what we first talked about, was the density function. M, the total mass of the function here, sorry, the total mass of the lamina, total mass of the surface, is going to be just the integral over this region of the density function. Oh, okay. So you can put some D's here for the domain of the region. Okay, yeah, that's it. So we can actually find the centers of mass now if we know the density function. That's it. All we need to know is the density function, and we can get the center of mass. So let's do one of those. Let's put it all together and find the center of mass for this thing. Okay, for this lamina, this surface. We're going to do a fairly easy surface to start off with, because this is a boatload of work to try to get all this stuff. Okay, but it's all good. Okay, why? Because we have to do, in order to do any of these problems, we have to do 3 double integrals. 3 of them. They're not all easy either. Okay, so let's see what we got. Okay, find the mass and center of mass, okay, of a triangular region with vertices (0, 0, 1, 0, and 0, 2. Okay. If the density function is rho of xy equals 1 plus 3x plus y. Okay. Okay, so let's look at what D is. What's the region that we're integrating over? Okay, the region that we're integrating over is going to be 0, 0 to 1, 0 to 0, 2. So this is 2, this is 1, and it's a triangular region that goes here and here, I think. Right, and then here. Okay, so you get that right? Okay, maybe I'll make this a little bigger. I don't know. Okay, so 0, 0. So let's space this out really nicely. Okay, that's 2. Okay, and then go away. Go away with your badness. My what is running low? Oh. There we go. That makes a difference. Okay. Great. Okay, so now we've got this thing here. Okay, so what's the equation of this line? What's the equation of that line? Well, it's y-intercept of 2. Okay, and what's the slope here? The slope, we're going to go down 2 over 1, so that's -2. Down 2 over 1. Okay, this is the region that we're looking at. Okay, so down 2 over. Okay, and then if I want to take a vertical slice here, okay, if I want to do dy dx, okay, a vertical slice, that means that y's are going to go from what? They're going to go from 0 to negative 2x plus 2, or 2 minus 2x. I'll just do 2 minus 2x. Okay, and the x's are going to go from 0 to 1, right? 0 to 1. And so if I want to find just the mass, okay, just the mass of this lamina, okay, what's the total mass of the lamina? I'm just going to plug in this guy here. Okay, so the mass is equal to 1 plus 3x plus y dy dx. Okay, so let's solve that. Okay, let's find the mass first. I'm going to have to divide by, then I'm going to have to divide the moment by the mass. Okay, the moment by the mass. Okay, at the very end. So what's the mass? The mass is going to be 0 to 1 of, let's integrate this thing with respect to y. Okay, so this is going to be y plus 3xy plus y squared over 2 from 0 to 2 minus 2x. Okay, so 0 to 1 dx. Okay, so this is going to be 2 minus 2x plus 3x times 2 minus 2x plus 2 minus 2x squared over 2. Integrate that from 0 to 1 dx. Maybe I'll clean this up a little bit. This is 2 minus 2x plus 6x minus 6x squared. Okay, plus, this is 1/2. 1/2. This is going to be 4 minus, what is this? 8x minus or plus 4x squared. Okay. That's it. This is going to be 2. This is going to be 4x minus 6x squared. This is going to be plus 2 minus 4x okay, and then plus 2x squared, right? Okay. So it looks like those cancel. I'm left with 4 minus 4x squared. Okay. So now let's integrate that from 0 to 1 dx. So this is going to be 4x minus 4/3 x cubed, 0 to 1. So this is 4 minus 4/3, which is going to be 12/3 minus 4/3, which is 8/3. Okay, so the mass is equal to that. Okay, so that's the mass. That's the total mass. Okay, it's 2 1/3. Or sorry, 2 2/3. Okay. Okay, so what's x bar? What's the x bar here? Well, x bar is equal to 1 over m times the integral with respect to x rho of xy dA. Okay, so we're going to integrate now with respect to x here. Okay, so what do I want to do? Do I want to do dy dx, dx dy? Okay, if I'm integrating with respect to x, okay, then I want to leave x as a variable as long as I can. So I'm going to do dy dx. Okay, I want to leave this guy to be, I want to leave that guy to be a constant. Sorry, I should say constant. Constant as long as I can. Okay, and so I don't want to have to do integration by parts if I don't have to. Okay, so so this is going to be x times, what was the original function? 1 plus 3x plus y. So 1 plus 3x plus y. Okay. times dy dx. Okay, and then we're going to do same limits of integration, 0 to 1 and 0 to 2 minus 2x. And this is going to be 1 over m, but 1 over m is just a reciprocal of 8/3, so that's 3/8. Okay, so now just distribute this and let's integrate. Well, this is x plus 3x squared plus xy. Okay, integrate on y, and we're going to get xy plus 3x squared y plus xy squared over 2. Okay, and evaluate that from 0 to 2 minus 2x. Okay, so this becomes x times 2 minus 2x plus 3x squared times 2 minus 2x plus x over 2 times 2 minus 2x squared. Okay, so this becomes 2x minus 2x squared plus 6x squared minus 6x squared minus 6x cubed plus, this is going to be x over 2 times 4 minus, that's my 8x again, plus 4x squared. Okay, so we get 2x minus 2x squared. Well, let's combine this. This is plus 4x squared minus 6x cubed. This is going to be plus 2x minus 4x squared plus 2x cubed. So let's combine my terms here. This guy cancels with that guy. That's going to be 4x minus 4x cubed. Yeah, that's what that is. Okay, and then we're going to integrate that. Keep in mind we have the 3/8 out in front. We're going to integrate that from 0 to 1 dx. Okay, nice. So now we're going to get x squared, 2x squared, okay, minus, this is x to the 4th from 0 to 1. It's kind of cool. So this becomes 2 minus 1, which is 1, times 3/8, so that's 3/8. So x bar is equal to 3/8. Huh, okay. So what does this mean? The x bar is equal to 3/8. Well, let's look back at our original diagram here. I'm gonna make it super big diagram. Oh, look at that. Okay. So this was at 2, this was at 1. Okay, and it says, look, at 3/8, well, 1/2, 4/8 is 3/4. If we're to cut this into eighths, right? If we're, is that right? Yeah. If we're to cut this into eighths, we would be at 3/8, right? So somewhere along 3/8 is going to be my center of mass. Somewhere along the x value of 3/8 is going to be my center of mass. So I want to know where on this triangle can I stick my pencil? Where am I going to stick my pencil so that when I spin it, it will spin evenly? Right? And I know that, well, at the x value of 3/8, it's going to be along that trajectory there, that linear path. Okay. Now I just need to figure out, well, where's the y value, right? Where's the y bar? Okay, to get the center of mass here. Okay, so the y bar is going to be the same thing, except we have to do y. Okay, so let's do that real quick. Y bar is equal to 1 over m times, okay, times 0 to 1 of 0 to 2 minus 2x, okay, of y times 1 plus 3x plus y dy dx. I'm just going to do dy dx. I'm not going to change limits of integration here because each of these are just their own term. And so I can integrate them term by term, and I don't have to worry about, the product rule or any of that stuff, or integration by parts, I should say. Okay, which is the undoing of the product rule. So this is going to be y plus 3xy plus y squared. Okay, so now let's integrate that with respect to y. This is y squared over 2 plus 3 halves xy squared over 2 plus y cubed over 3. Evaluated, okay, from 0 to 2 minus 2x. Okay, interesting. Okay, well, I can factor out a y squared out of this, right? So y squared. Okay, so times, what do we get? We get 1/2 plus 3 halves x plus 1/3 y. Okay. So just make it easier to evaluate if I do this. Okay, so this is 2 minus 2x squared times 1/2 plus 3 halves x plus 1/3 times 2 minus 2x. Okay, that's when y is 2 minus 2x. Do I need to deal with the 0? No, because what happens when I plug in the 0 here for y squared? It just goes to 0, so I don't have to worry about that one. Okay, so what does this become? This becomes 2 minus 2x squared times 1/2 plus 3 halves x plus 2/3 minus 2/3 x. Okay, it's interesting. Okay, so what's 1/2 plus 2/3? 1/2 plus 2/3, we've got to change those to sixes. So that's 4/6 and 3/6 is 7/6. Okay, so this is 7/6 plus 3 halves minus 2/3. Change that to 6 as well. That's going to be 9/6 minus 4/6, which is 5/6. So this is 5/6x. Okay, times 2 minus 2x squared. Oh, okay, so that's the integral on that one. 1 over m, that's 3/8. And then this is going to be from 0 to 1 of this thing here, dx, right? Okay, now I could do integration by parts here. I don't really want to, so I would just multiply this all out. If you multiply this all out, I'm not going to spend the time on it here. It's a waste of time for me to multiply all this out. But if you multiplied all this out, you would get the following. You would get 10x to the third minus 2x squared, sorry, 10/3 x to the third minus 2x squared minus 6x plus 14/3 dx. Okay, and then you're going to get 10/12 x to the fourth minus 2/3 x cubed minus 3x squared plus 14/3 x, evaluated from 0 to 1. Okay, multiplied by 3/8. And then we get 3/8 times, this is 10/12, which is 5/6, minus 2/3, plugging in 1, minus 3 plus 14/3. Evaluate all that, that comes out to 3/8 times 11/6. Change that all to 6. And then we get 11 over 16. Okay, so 11/16 is where the y value is. So y bar is equal to 11/16. So where's the center of mass? The center of mass, okay, was at 3/8, 11/16. Oh, okay. So again, going back to our original lamina here, okay, based on the density function they gave us. Okay. Now, if it was uniform density, it'd be a whole lot easier. But that's like spitting a piece of paper. But it's not uniform density, so it's a whole lot harder. But we do know that the y value, okay, the y value is where? It's 11/16. 11/16, which is, okay, where's 11/16? Well, 16/16 is right here. That's 1. Okay, that's 16/16. Okay, 8/16 would be here. Right? And so where's 11/16? So 11/16, I don't know, I don't want to divide this into pieces of 8, but that was a pirate reference. Pieces of 8. Okay, and so 1, 2, 3, 4. So we got 8 pieces now. So 1, 2, 3, 4. Sorry, I want to go 3 because this is 11/16. So I'm just going to eyeball it and say, it's right here. Okay, and where's that center of mass? That center of mass is at 3/8, 11/16. Okay, that's the center of mass. Boom, nice. Again, these problems, super fun if you like to do double integrals, because it's to do one problem, it's 3 double integrals. And sometimes the double integrals are not very fun. So it's good times, okay? Grab yourself like a salad and a root beer and then do your homework, just enjoying all the double integrals, okay? And this is how you actually get better at doing double integrals. You do problems like this, okay? Now, a moment of inertia, okay, moment of inertia, okay, or the inertia of a particle's inertia, okay, or what we call it, the second moment of inertia of a particle, we should say, of a particle, okay, about the x-axis, or with respect, it should say with respect to the x-axis, but we'll just say about the x-axis is I sub x, which is equal to now y squared, okay, rho xy with respect to the density dA, okay, and then I sub y is the same thing, but now x squared rho xy dA. So about, excuse me. Right. Just leave a message. Okay, about the y-axis, okay, is this guy here. Okay, IO, okay, is also called the polar moment, okay, the moment of inertia about the origin. We'll just do about the origin, okay, IO, okay, is equal to, this is also called the polar moment of inertia. This polar moment of inertia is this guy, x squared plus y squared times rho of xy dA, okay? You can see why it's the polar moment because this is r squared, okay? Which is actually r cubed. Okay, it's r cubed, not r squared. Why is it r cubed? Because if you change the polar coordinates, you're gonna have to have an r, d theta. You gotta have the extra r, okay? It's no laughing matter, r d theta. Okay, So this thing is called the Pullock moment. And note what? That this is separable. I could separate this into two double integrals. I could separate this into a double integral involving x squared, okay, and a double integral involving y squared. Oh, well, isn't the double integral involving x squared iy? And isn't the double integral involving x y squared ix? Yeah, I can just say note that the moment about the origin is the sum of these two. Okay. Okay, find IO. Okay, last example. Find the moment of inertia about the origin of a homogeneous disk with density rho of a homogeneous disk of density rho. Okay. Center the origin and radius A. Okay, so it's a homogeneous disk of radius A. Okay, and this disk has a homogeneous density. It just means that the density at any point is the same as any other point. Think of it like a piece of paper, okay, or any other homogeneous. Think of it like a piece of metal, okay, all made out of the same metal. Okay, so this is homogeneous. So we're just saying that it has density rho. Okay, then rho is just some constant density, like maybe 2.5 or 2.37 or whatever it is. Okay, it's a constant density rho. Okay, so what's this going to be? Well, this is going to be IO is equal to the double integral, okay, of x squared plus y squared dA, right? Oh, sorry, rho xy, sorry, times rho xy dA. Okay, so in this case, okay, this thing here, if I change this to polar coordinates, then I would get, okay, because it's around a disk, it's going to lend itself to polar coordinates. This is going to be r squared times the density, which is rho. I'm just going to make it rho. Okay, times r dr d theta. Okay. And what's r go from? R goes from 0 to a. And what does theta go from? 0 to 2 pi. Oh, okay. So this is really rho, which is a constant. I'm going to pull that out. Rho is a constant, okay? And 0 to 2 pi, 0 to a of r cubed dr d theta. So this is going to be r to the 4th over 4, 0 to a. So this is a to the 4th over 4. Integrate from 0 to 2 pi. D theta, okay, so this just becomes 2 pi a to the 4th over 4. So this becomes pi over 2 a to the 4th times rho. So this just becomes pi rho a to the 4th over 2. That's it. That's what IO is. IO is equal to this. Now, since this is a homogeneous disk, then the moment, right? So since it has a lot of symmetry here, okay, and it's a homogeneous disk, okay, I know that Ix is the same as Iy. Okay, the moment of inertia of x with respect to x is going to be the same as the moment of inertia with respect to y. Okay, from symmetry. Okay, so we know that Ix is equal to Iy from symmetry. Okay, and so And we also know that IO is equal to IX plus IY, okay? And so IO is equal to 2 IX's, so IX equals IY equals IO over 2. Okay, so what is IX? Well, IX is going to be equal to pi e a to the 4th over 4, and that's going to equal IY. Okay, and then is that it? Yeah, that's it. Okay, and if we want to find the mass of this thing, we could do it in terms of the density. The mass is the density times the area. Times the area. Okay. Think of the total mass as the integral of rho, right? dA, right? So m is equal to this. Well, this is just a constant. So this is really just rho times 1 dA, or d, right? d1 times dy dx, dx dy, dx dy. Okay, and then what could we do? We could say, oh, well, this, if we want to change the polar coordinates, this is going to go from 0 to a, 0 to 2 pi, r, dr d theta. Okay, nice. Okay, so this is going to become r squared over 2, evaluated from 0 to a, which is a squared over 2. Okay, and then that integrates 0 to 2 pi, which if I just d theta, if I do 2 pi times a squared over 2, that just becomes pi a squared, which is just the area of a circle with radius a times rho. So does that make sense that the total mass would be the density times the area? Well, yeah, and what was the area? The area was pi r squared. It was a circle. So we just actually found the area of a circle using double integrals. Okay, we actually proved the area of a circle in calculus. So there you go. And also, since I proved that, I'm going to stop there for today. Okay, that's enough. That's enough for me to do. Okay, I just proved the area of a circle. Right, over a circle. Right, with uniform density. Let's let the density be 1. There you go. Interesting. Okay, because what's the circle? Right? X squared plus y squared equals r squared. That's the equation of a circle. General equation of a circle. Centered at the origin. Okay, so we just did the proof. Which you can't do any proof. I mean, you can do approximations of the area of a circle, but in order to prove it, you actually have to do it this way. You have to use a double integral. Okay. So. Okay, I will see you guys when? Monday? Okay. See you Monday.
Bye. Thank you.
Thank you very much. I'm glad you guys are taking this class, synchronously. I couldn't imagine taking this class asynchronously. Just trying to teach myself this stuff. That would be really difficult.